Welcome to the Value Maker podcast. My name is Purvis. I'm your host, supported by Heather Bicknell, as we meet with the people that make the digital workspace work. It's about the technology, it's about improving people's work experience and finding the return on value. Steve, welcome to the Value Makers podcast. Do you want to introduce yourself, please?
Great to be here, Ryan. I'm Steve Orrin. I'm the federal CTO for Intel Corporation. And basically in that role, I help the US government and public sector understand and adopt technologies and architectures to meet their mission and enterprise needs. We help them understand both what Intel as well as their ecosystem that we support technologies, platforms, and products and software can do for them. Help them customize these technologies and architectures to meet what their actual needs are and how they can successfully deploy both what's available today and be planning for what's coming in the roadmaps.
Fantastic. You answered the first question I'd ask, which is what value do you offer? But I'm actually quite surprised as Intel, you almost sound like a consulting business as opposed to a chip maker.
It's interesting you say that. So Intel is an ingredient provider to everybody. When we say Intel inside, we really do mean it. Our technologies, architectures, our CPUs and software are literally in everything, from your laptops and edge computing through the network, both wired and wireless, all the way up into the cloud and data center. And typically organizations purchase our technologies via OEMs and channels like Dell or HP or Supermicro, or as consumed through the cloud providers like Amazon, Microsoft, Google, what have you. And they're using applications, whether it be databases, web applications, transaction systems that are running on top of Intel. So most of our job really when it comes to engaging directly with customers is, like you said, it's more consultative or influence, as well as really we're there to help. Because again, I'm not trying to sell anything directly to the government or to an end customer. Our role is really to be there as an advisor, to help them understand both our technologies as well as where technology innovation is going, help to understand what their mission requirements are, what their problems and challenges, what they're trying to accomplish, and make the right technology for the right compute for the right application. So it is much more of a consultative role, as well as we can get our hands dirty and get in there and help develop custom solutions with them for their mission areas, for their enterprise needs, and be able to provide that at scale.
While you were speaking, I was thinking of the analogy, you skate to where the puck is going to be, as opposed to where it is right now. And by being that helper, the trusted advisor, you're starting to get your R&D sort of for free in that respect, because you know what the customers want in the future.
Exactly. And it's an interesting sort of two-part role. I spend a lot of time with the government customers, understanding their requirements, their needs, helping them understand what technologies we have. That's the outbound side of it. At the same time, I also then can take those requirements back to our business units, back to our labs and research of it and show them where our customers are, where they're going, and help make sure our products meet their needs, both current and in the future. Bi-directional role in that respect. And it allows us to not only, like you said, not only help them skate to where the puck is today, but also both sides to know where the puck is going and to be ready for that so they can be successful.
Yeah, no, it makes a lot of sense that you're doing it. But I never thought anyone was doing it, to be honest. So, and tell me, when you talk about the technologies of Intel, laymen would expect Intel's just chips. What else have you guys got that you want to explain to people when you meet them?
Sure. So we are known for the chips, and the chips are driving every technology innovation out there: 5G, AI, cloud computing, edge sensing, and edge computing. So our chips are behind all of that technology. And it's more than just a generic CPU in that respect. They're inside the Intel architecture, inside the instructions are accelerations and specific capabilities that enable those use cases. So you run your AI or your database will run faster on Intel because we've programmed in specific instructions. We've built software interfaces to help the ecosystem adopt those technologies to be able to accelerate performance or to provide advanced security for those application spaces. We also provide a variety of hardware capabilities. So we're known, like I said, for our CPUs and the laptops and the servers, but we also have FPGAs with our Altera subsidiary. We also have accelerators for AI. Recently announced the AI PC has built-in chip specifically for accelerating AI as part of that CPU package. So it comes as part of the CPU. And then in the data center and cloud environments with our Gaudi architecture and our GPU architectures, being able to accelerate both AI workloads as well as broader use cases, high performance computing use cases, leveraging specific architectures. Other areas where we innovate is in the 5G space. A lot of the 5G infrastructure that is that your phone will be connecting to is actually running on Intel technologies. Our innovations in the enterprise and cloud network, where we've got what's called an IPU or infrastructure processing unit, is a radical approach. When you look at it, it's moving a lot of that compute that would normally happen in the CPU right into the network plane so that you can do a lot of your network workloads at the back plane of the server or in the network infrastructure, offloading that work from the CPU itself and allowing your network to become intelligent. And so when you think about the cloud scale routing or being able to do deep packet inspection at scale or intelligent routing capabilities, intelligent protocol manipulation, a lot of that work can now happen at the back of the computer, if you will, in the backplane network, offloading from the CPU. And so that innovation of the IPU is changing the way that cloud computing and enterprise hybrid cloud computing is happening by allowing the network to be both intelligent and more functional. Again, allowing your CPU to do your mission, run the database, run the transaction server, and then putting more intelligence in the network. All those innovations are part of Intel's portfolio that we bring to market. And again, it's our job to help organizations, both large and small, take full advantage of those technologies and capabilities. The other thing that people don't really know Intel for as much, unless you're working directly with us, is our software. Intel at any given time can be one of the largest software providers in the market. We have about 20,000 software developers, and they build a lot of the software that you don't see, but it's actually what makes VMware or the cloud or Oracle or other products run best on Intel. We build that interface layer, we build acceleration, and we build end user software. We build AI tools and frameworks to help developers get best use out of their existing and future architecture. Things like PyTorch and other frameworks are contributed to by Intel. We have one of the largest open source teams that deliver open source from the Linux kernel all the way up through standalone projects. And then an area we've been innovating in for the last couple of years has been providing software tools to be able to do security at scale, to help organizations take advantage of both hardware-based capabilities and software capabilities to do attestation, to be able to verify where is my workload running and how secure is it at a given time? Can I verify that CPU? Can I verify that cloud instance? Can I make sure it's running in a confidential computing container? So that infrastructure software called the Intel Trust Authority is a software stack that both cloud providers and end customers are leveraging to be able to verify their security status of their application and their data as it transits across these networks and infrastructures. It also is being applied today to AI workloads. How do you know that your AI inferencing model that you spent millions of dollars training is protected throughout its life cycle? And so a lot of that core software infrastructure is actually built by Intel. And again, oftentimes people don't even realize it, that they're taking advantage of Intel software when they're running their systems. They see Windows, they see Linux, they see the cloud infrastructure. There's a lot of software behind the scenes that Intel's actually building and deploying.
Yeah. When you explained the IPU, I think it was the network intelligent piece. I was wondering about how much of that was software defined as opposed to written into the chip itself. And could the chip carry on do what it's doing, but you could change the interface layer because it's programmatic.
And so really the thing about software defined networking and and it's not your mother's software defined networking, if you wanted to take it that way. The old model of software defined networking was a virtualization only based model. And what we've seen is if you take that to the next level, where I can build that intelligence into the hardware and provide a software interface for being able to do the SDN or the SDR kind of things, where you're doing software defined, but leveraging hardware acceleration or leveraging compute in the network. That's really one of the big shifts in things like IPU is it's where you're doing that software defined networking, where you're applying those virtual appliances or the virtual network functions by being able to have a compute node, if you will, in the network itself, as opposed to just offloading more, taking more of your CPU time to do the networking function. So you're really doing a lot of the same software defined networking functions and administration and protocol manipulation, but now you're doing it in the network card or in the network backplane, but with the same functionality and accelerated with dedicated hardware. And I think that's one of the examples that we've got is that if you actually pop open the network card and you were able to look at all the components, you'd see an actual CPU in there. So you now have a full computing stack that has its own Linux kernel, if you will, running in your network separate from your CPU. And what's really powerful from both a networking perspective and a security perspective is that by having that intelligence in the network, I'm getting better performance from my actual applications, because I'm offloading that from the CPU. But also when you think about the security perspective, if I'm doing like high-speed deep packet inspection and I'm detecting malware threats, I'm detecting them before they ever make it to where your data is resident. I'm detecting them at the edge of the network long before it could ever cause any bad effects on the CPU. Long before even from a denial of service, you could catch that before it ever affects your application workloads. And so by separating those worlds and allowing the network to do what the network's really good at, where the network wants to do it, but with that same sort of software-defined approach just now in the network. And so that separation is really how you, if you look at the cloud scale of how you get to the kinds of scales we're seeing in the cloud, as well as the enterprise data centers with the hybrid approaches, by being able to separate the network from your application and data workloads, you're getting better performance, but you're also getting a much stronger security value proposition by being able to separate those worlds out and apply the security where you need it, as opposed to waiting in the logical sense for it to come to the CPU itself.
Yeah, that resonates in the edge computing is something I've worked on for years. And what you're saying is almost it's distributed computing in a more granular way.
Exactly.
So it makes a lot of sense. Like the original sound cards became smarter and smarter with their own processing.
Exactly. And eventually they just got built in, and now every
Mm.
computer has a sound card, but it's actually a chip that accelerates that capability built into the package. And that's really the of evolution we see across time as functionality becomes more scale and more ubiquitous. To get the performance and to get the operationalization you need, you want to scale it into hardware and make that ubiquitous for everyone so that you have a common architecture for all the software to leverage.
It's a lot to maintain, though. It's the more you distribute and the more you come up with these segmented components to maintain them and make sure the interoperability of them works. What is your quality process like?
So it's interesting you talk about that. You would think that it becomes harder, but that's where really both software and our ecosystem enabling teams really come into play. One of the reasons why Intel invested over 20 years ago into ecosystem enabling as a dedicated function is we build the hardware, we build these capabilities, but how does an end customer actually take advantage of it? You don't want to have to train every company on the planet how to use a distributed network node or a new Wi-Fi protocol. So by creating this software layer and actually having our teams work with the ecosystem, with both the startup community all the way to the established commercial and open source, and help build that interface and build that abstraction layer and create that interoperable standard. And one of the things that Intel has done its entire life is develop industry standards that everyone takes advantage of. USB was created at Intel.
Really?
Exactly. We have one of our former fellows who's since retired was the creator of the USB standard, but we didn't keep it as a proprietary standard. The whole point was we want to enable ubiquitous computing. Wi-Fi was first put into Intel platforms as a Wi-Fi accelerator to help drive the industry adoption across all platforms. And so one of the things that Intel has been known for is developing these core infrastructure standards to help with that interoperability so that all computing platforms, both Intel as well as our competition, as well as other chip providers, have a common architecture, because more computing, more leveraging computing benefits the entire industry.
For sure.
And for that interoperability, by having an ecosystem team that's working across all the different, if you will, competitors and ISVs and open source tools, we're able to see the nuances of how people are implementing different protocols and create that sort of common infrastructure layer to alleviate a lot of that interoperability that we saw back in the 80s and 90s as things were first starting to come out. You had to go all in on a particular platform. Creating common standards and common ecosystem enabling really allows everyone to build their differentiated capability on a common architecture. And that's where x86 is being the common architecture across standardized computing is really driving the innovations we see every day.
You mentioned high performance computing, but you didn't mention quantum computing.
I didn't mention it. There's no reason. Quantum computing, it is a next wave that everyone is really looking at. No one knows exactly when the date will be where we have a practical quantum computer. The NIST and others are looking at, is it 10 years from now? Is it 5 years? What's important, though, is that quantum computing is going to be one of those next big wave of computing capability. Now, I don't believe that every laptop will have its own mini quantum computer. That's just not practical. However, we are going to see in the future high performance quantum computing is really solving those next big, whether it be AI challenges or simulations or deep space analysis kind of things. And one of the things where they're in the quantum computing race, you have a lot of universities and some very big organizations and governments all looking to build that big quantum computer. And it's a beautiful, exquisite thing with cryogenics and beautiful pictures are taken. And I think that that is a lot of wonderful research as everyone races to get the next qubit-sized quantum computer. Intel's approach is actually an interesting one. We're looking at not how can you build the biggest chip in an exquisite lab that's a one-off, really cool science experiment. We're looking at how do you scale quantum computing? How do you make it
Mm.
available? And we're taking a dual path on that. So if you go back and you look at the press releases that multiple people did around their quantum computing, you see the exquisite computer. When Intel did its press release and had all of its pictures, we had the exquisite computer with the Tangle Lake chip. That was the code name of the chip. And I believe the first one we went out with was like 11 qubits, and then we have a bunch higher qubit one in our next generation. But actually the most telling picture was like buried on the bottom right. And that was, there was a rack of servers that were all running. And then there was one server with a really long extension. And what that rack was, that was our testing and validation set. Basically, where every Xeon system, all of our server products go through their final stage of testing and evaluation. They go through it, they get plugged in and they get tested and they get verified that they're meeting to the performance and functional requirements. And they're on the top right of that of a set of rack of servers was the quantum chip going through the same validation and test. And what we showed is that you can use existing processes, our existing quality and validation test processes for quantum chips. We're trying to show how you scale quantum computing chips, not can you build the most exquisite science project. So that was one big innovation, is that we can use our existing manufacturing processes to produce quantum chips like we produce data center chips. The other was looking at the software stack. So we can all build really cool quantum chips, but how do you write a quantum algorithm? How do you take your existing AI and port it, if you will, to a quantum system? It's a completely different architecture, and really it's very different math, all the way down to the CPU level. And so one of the things we did is we took not only our quantum, we created a simulation for it and built a software, an SDK that we then opened up to universities and to corporations and to the governments globally to be able to come in and try their algorithms on a quantum processor and be able to give people the ability to start coding towards quantum, as opposed to just, well, this is a really cool project that MIT or Google are doing. So we're looking at it from those two perspectives. How do we, when quantum happens, how can we scale it so it's not one chip, but millions of chips that are able to power that next generation quantum computer? And then I think one of the really cool things is how do we get both existing scientists as well as the next generation of university researchers and students access to quantum SDKs so they can start building that next generation of, if you will, questions we want to ask a quantum computer and do it in a quantum way. You can't just take your math problem today and just dump it on a quantum computer. You're not going to get the efficiency. But if I ask the right quantum style question of a quantum computer, that's when the magic happens. And so we've been providing that support for quantum development in parallel to a lot of the innovation around quantum computing. So I see quantum as really exciting future area, and Intel's investment is really how do we make that ubiquitous when the time is right?
Yeah, and I think there's probably ethical considerations too. A lot of the original hype that I saw was around cracking of passwords and encryption. And you've got to, it's the same as AI needs to have some level of governance. Some of the stuff has to come out with scalable governance that's in place, I think.
Yeah, and it's interesting. There's work, and we've been participating in the NIST challenges as well as helping the NIST organization understand the performance impacts of the post-quantum. So we think about quantum computing is really the goal there is let's do some really cool science. Let's scale these applications, do high performance computing on quantum systems, get much faster time to data. We want to be able to do weather modeling, and we'd like to be able to know where the hurricane's going much sooner than what we do with our current models. There's a lot of really cool research that is really for the public good. Things like earthquake detection, forest fire tracking, a lot of these sort of big problems that we're using high performance and cloud computing today, and we're getting okay results, but it would be quantum computing offers the opportunity to get faster results, more accurate results. And what that means is we can then be better prepared for the hurricanes that are coming, be able to know when a volcano is going to erupt or when an earthquake is going to happen. Or some of the more fascinating things about our life of understanding the dynamics of quantum or cosmological events and be able to really understand the sheer volumes of data in a more efficient way. The flip side is, like you said, that quantum computing is going to impact cryptography and the things that we rely on to secure the internet and secure our data. That is one of the big challenges of our day. And what's going on right now across the industry and across the world is a drive toward the next round of encryption algorithms and key sizes to support quantum resistant cryptography. And that's going to be, there's been both the move by NIST and global governments to put out what are the recommended key sizes for symmetric cryptography. And symmetric is sort of the standard shared key amongst individuals. So what we had is AES for the last number of years. Now we are increasing the key sizes for those. But then looking at the digital signature algorithms, the public key crypto, that has to change. So RSA, Diffie-Hellman, those public key cryptography that are used in everyday web browsing, those protocols don't actually do well in a quantum relevant world because quantum opens the door to some unique attacks that
Mm.
really remove the security parameters that we've assumed for public key for many years. There's certain properties of those public key algorithms that have been around for many years that make them hard to crack and make them secure. There's an algorithmic approach that when you have quantum computing, those assumptions go away. So we need new algorithms. Those new algorithms have finally been announced and are being implemented. And so part of the efforts that Intel and the industry are working on together is to implement those algorithms into the hardware and software so that they are just in there like the current crypto algorithms are. Now, one of the challenges of post-quantum cryptography is the algorithms themselves are significantly slower from a performance perspective than the predecessor algorithms. And part of that is because it's a new kind of math. And part of
Mm.
this, we've had 40 years to really make public key crypto very efficient in hardware. We're all chasing that, trying to get to that same level of efficiency in a much shorter time frame. So Intel and our competitors, we're working together as an industry to help create the most optimized implementation of these post-quantum crypto algorithms and get them implemented in hardware with acceleration built in so that when you want to flip from legacy crypto to the post-quantum crypto, you can do so without significantly impacting the performance of your applications and your workflows in your network that want to take advantage of it.
Yeah. You mentioned acceleration a lot. So what actually is acceleration, if you had to explain it simply?
Sure. So acceleration, at the end of the day, you can do computing on any platform. A key example, you wouldn't want to run, let's say, Windows 11 on a 10-year-old laptop. It would
Yeah.
grind to a halt. And part of the reason is that Windows 11, A, it's huge. B, it's got a lot of things that it relies on in order to be able to provide you that experience and to run all the tools and to run AI and everything that comes in there. So what Intel and our industry has been doing over the past 50 years is adding hardware features into the platform to accelerate the functions and the workloads that are running on top of it. We make software run better by having it optimized in hardware. And that every generation of new hardware makes everything faster. Now, in the chip world, you have the classic model, which is what we want to reduce the amount of size and power, and increase the number of transistors. And that's a Moore's law that we reduce the size by increasing the number of transistors. You get lower cost, lower power for more compute. And that's been Moore's law since it was created back in the 70s and 80s. However, there's another angle to that. It's not just how many more transistors can I put in there, but it's what are those transistors doing? What are the actual algorithms and functions that I can hard code into hardware? And when you think of it, you pick sound as an example. In the early days, you had sound was just run in software and it was very slow and clunky. And then they created dedicated cards that were about yay big. They were a good 6 to 8 inches that you had to plug into a desktop to accelerate the sound functions, the things that generated sound, that turned digital into analog and back again. What Intel and the industry has done is we take the actual algorithms that were being implemented to do that digital to analog digital, and to accelerate and to provide the quality, and we code that into instructions, put that into silicon inside the CPU, and then provide if you will, an API, but it's really an instruction for software to say, I want to be able to do that function, and then the hardware does that function on behalf of software. So acceleration from a hardware perspective is basically taking what was a software function, turning it into a hardware function, and then providing an interface to the software to offload that work to the hardware. And we see this in every aspect of our computing. There's, obviously there's media transcoding and media acceleration. There's cryptography and security acceleration. So the math behind cryptography is actually a lot of work. It's a lot of steps to do cryptography. Putting that in hardware makes the process super fast. A lot of us, a lot of people who are around today don't know what it was like to run cryptography back in the 90s when it was super slow and it would add 20 to 50% overhead on top of your computer in order to be able to turn on encryption. Today, no one even thinks twice because it's a non-issue. There is no performance impact. And part of that is because all of that hardware that's accelerating that cryptography has taken those crypto algorithms and been implemented in hardware. In the last 3 to 5 years, AI, you can't go anywhere without talking about AI. Why is AI happening today? Obviously, we have a lot more data to consume so we can drive it, but we've had these algorithms for 40 years. AI as a concept isn't new. What's changed is the hardware got good enough with acceleration and built-in functions to perform the AI in a fast enough way where I'm not waiting 6 months for an answer, where I can do a chat GPT and get an instant response. The way we get there is not because I've got some better algorithm. It's because the hardware is able to perform those functions on behalf of the software. And that's really at the core of what acceleration is and optimization. It's allowing for the workload or allowing for the flow that you're trying to implement to happen at speed and at scale because the hardware is offloading what was once a software function.
That's still a lot of information. So the thing that fascinates me is, I'm going back to when I studied computer science 10, 12 years ago. We used to have the concept of the E, which would be, and you had a read-only module, then you had the programmable module, etc. Are you building chips that are programmable, that are being updated with new instruction sets? Or is this still a case where it's been written into the chip once and once only? And I'm thinking about this from a security point of view and authenticity more than a practical reuse of the chip.
Ryan, I would say that the world is much more complex than it was 10 years ago when it comes to chip architecture. The way to answer that is the chips themselves are hard-coded silicon information.
Okay.
And what defines programmability is really a nuanced answer. I want to put FPGAs off to the side because I'll get to that in a second. But you're talking about a classic CPU, whether it be a laptop CPU or a data center CPU. There is, hard IP that's in there that runs specific functions, and it is hard coded like you described. But there's a lot of things that go inside a chip that under the covers that are actually software that can be reprogrammed or that can be tuned post manufacture. So a lot of times what you'll find, and let's take the example of in virtualization environments, there are places in hardware that can be changed, manifests and soft memory that can be leveraged. One of the other things to think about is cache. That has changed the game. So in the old days, you had a little bit of cache, and that really allowed you to be able to swap things in and out of memory. And that was all it was really good for. Today, we have data center products that have gigabytes of cache memory. That means the CPU itself has a gigabyte or more of actual flushable cache that it can use for doing more than just, I'm holding onto it to goes to memory. You can actually do programmatic things in your cache to optimize the workflows, to reorder the data.
So just a question on that. So that cache memory, is that a special kind of memory, like a flash memory or something like that?
It's a special kind of memory inside the CPU. So it's a high-speed memory that is native in the package. So it's at the end of the day, when you look at it, if you were a silicon architect, you'd say, well, that's a memory type. It's not like your DDR, which is like your add-in card, or an SSD, which is a storage device. It's a hot memory, but it's basically the same architecture of memory. But it's built into the CPU. And actually, if you look at our current heterogeneous architectures, there's multiple memory banks spread around close to the compute node. So each one of the cores has its own access to memory banks.
Because that's what I'm going to ask you. Is the important piece is how close they are to the computing unit.
Exactly. It's about reducing latency and giving better performance. And by being able to miniaturize, and that's one of the real powers of the modern architecture. It's no longer the monolithic chip that we're used to from the old days. It's actually if you were to pop open a chip and be able to look at the thing, you won't see one massive die like you would 20 years ago. It's actually a bunch of little dies that are put together into what we could refer to as a heterogeneous or multi-chip package. And you'll have dies in there that are compute cores. You'll have memory dies. You'll have network I/O dies that are specific for I/O, that are separated from the CPU. And again, it's all about putting the most accelerated compute together where you need it in the most efficient way so that at the end of the day, you want data to flow through as quick as possible to give the application the best performance. And so we've transitioned as an industry to a heterogeneous architecture within the chip. Again, it still looks like one big chip, but if you pop it open, there's multiple little chips in that are connected on a high-speed bus that allows for that interplay between the different compute cores, the memory, and these dedicated nodes. You pick on security, there's dedicated security engines inside that CPU package that can do authentication, that can do digital signing for firmware verification, can do crypto acceleration and offload, and has the ability for keys to be stored in there so that you can have root of trust keys that are provided at design time and root of trust keys that can be implemented by an OEM or by a cloud provider into the hardware so that I can lock my application to that platform and get that true security root of trust kind of mechanism.
So how would you explain it was FPGAs? That
Yeah.
the right?
So FPGAs, that's the other kind of computing. FPGAs are field programmable gate arrays. As a concept, have been around for a very long time. They are basically a programmable silicon. They're a set of, basically you would have FPGAs, a set of arrays that you can then implement software, and we're using the word software in quotes here. It's RTL, basically it's the low-level language of computing that can be modified by the end user. And a lot of certain special purpose applications, a lot of times in networking, in radio and communications, in media use cases and transcoding, where you want to be able to get highly optimized protocols implemented. And there's a lot of variation depending on what type of protocol you're talking to, what type of media transcriber you're going to. FPGAs are the answer. And the FPGAs we're dealing with these days, it's much more advanced than, again, the FPGAs you would have used in college when you were doing your early computer programming. They have fixed IP blocks. So one of the things that the industry has done in FPGAs is understood that there are certain functions you want that you're going to want to leverage all the time. You don't need to recode them. So those are hard IP blocks. A lot of that's around security, around certain transcoding or digital signal processing kind of workloads that are just common in the industry. And then for your particular application, you're going to order a lot of that stuff together in post deployment kind of use cases, or be able to update as your protocols change, be able to do from when we go from 4G to 5G, being able to use an FPGA to change the protocol without having to deploy new hardware is a very powerful thing. So FPGAs are part of that next generation of heterogeneous architecture where you want to be able to customize or get specific protocols optimized in hardware versus doing everything in software. Good examples of the software-defined radios, which we're seeing a lot of in the 5G space. We're seeing it in other edge sensing domains where I need to be able to be dynamic, even in a deployed environment. FPGAs allow me to implement that software-defined radio really as a hardware-defined radio, but with software as the mechanism, but leveraging the FPGA as my compute node. Where we're seeing a lot of the industry go in public sector as well as in the commercial space is looking at ways to bringing your classic compute and your programmable compute together in the same package. Something called, it's a type of multi-chip package where I could have classic computing, AI engines, software workloads running on a Linux kernel, paired in package with an FPGA where I could put in my unique algorithm that I want to implement, my waveform or my my transcoder. If I'm going to do certain kinds of media transcoding, I can implement that in an FPGA and then still talk to the classic compute module to do my workload. So what we're seeing, and this is the trend that Intel recognized a long time ago, and the industry is starting to catch up on, is that it's not a one-size-fits-all compute world. It's a heterogeneous compute world, and you want the right computing where you need it, when you need it, from the edge to the cloud. And having a diverse set of computing architectures enables people to get the best performance, the best security, and ultimately for the end user, the best experience.
I'm thinking a lot about blockchain in the federal space, or even global from an immigrant. So identity point of view, and passports is such an archaic mechanism still for travel. With what you're doing is facility with programmable chips like FPGAs and stuff. Are you finding application for that now? Because one of the problems with blockchain, I think, was the speed of adding to the block. But that seems to have been dealt with as we've improved, obviously, on technology. Any thoughts on that?
So I would say that blockchain acceleration, actually, you probably don't need to go to an FPGA, although you could go. For certain use cases, you may want to go with customized computing. But as an industry, we've already implemented algorithms into the classic compute, into the server nodes that accelerate the math behind public key crypto, accelerate the math behind blockchain. So the reason why we're able to do blockchain at scale today from a computing perspective is that a lot of that acceleration is already built in. You already have it if you're buying the latest generation servers. Where you see a lot of the challenge around blockchain is going to be twofold. One is in just the distributed nature. It's the network latencies between systems. It's the amount of data that I'm trying to move across those nodes. And then the other side of it is the being able to protect my blockchain. So while mathematically in the paper, it says, oh, these things are secure, real world gets in the way of security every time. And one of the things that people don't recognize is that while the blockchain algorithm itself may be really secure, every step of the way before you get onto that blockchain and then how it's managed across the entire node and how you do consensus, those are weak points. And so what I think you're finding in, especially if you take something as important as passport and travel or other financial transactions, the reason why it's still somewhat of everyone has their own self-contained and it really hasn't gone global in its interface is there's still some challenges to figure out of how do I secure the whole life cycle. And it's less about the algorithms or even the computing. It's about the processes or how do I verify that before I put data on the blockchain, that you're the right person to put that stuff on the blockchain. Do you have the authenticity? And that's where a lot of the stuff starts to break down. Or we say, oh, yes, it's got to be secure because I know Ryan. Do I really know you? What if someone stole your identity, put something on the blockchain? Now it's in there for good. Those are some questions that I think on a global scale, looking at the more life cycle approach to blockchain are things that people are working on today. There's work that I've been doing with University of San Diego Supercomputer Center on using some interesting approaches around machine learning AI to monitor blockchain activity, to look for potential fraudulent or coercive activities on a large scale blockchain node, to be able to help detect those kind of anomalies or aberrant behaviors that could be an indicator of either somebody trying to do something fraudulent with the blockchain or a group of people trying to influence or put undue influence on consensus or on some of this particular nodes, slowing down the node so that other nodes get preference is a real world problem, especially when we're dealing with financial transactions or authenticity, and you want to be able to game the system, if you will. And so there's a lot of work in the research side to help make the entire blockchain ecosystem better and more secure in a real world context. What we see today, a lot of the blockchains, they say they're global, but they're really still somewhat self-contained within their own domains. We don't see a lot of the cross-domain stuff yet, but it's coming.
Yeah, I can imagine it's still young. A lot of these technologies are very young. They've been around a while, but they're still very young in the context. What are your thoughts on your competitors, the Apple Silicon chips, the AMD, Snapdragon, those sorts of guys? Are you guys all in some respects competitors, but also friends because you're sharing common goals? Or
so there's a lot of competition out there. That's the best, best way to think about
that's
it.
the way to say it.
We, at the end of the day, a rich computing environment drives all boats. We want people using computers across every domain. We want people using the best AI algorithms, the best workloads, getting edge computing, pulling in all that sensor data. You want a healthy ecosystem. And today there is a very healthy ecosystem, both on the compute side, on the edge side, and in the cloud and AI side. So what we're seeing is a lot of healthy competition. At the same time, we've all recognized, and Intel and AMD announced a partnership a couple of weeks ago, where we're going to work together to help reinforce the x86 instruction set, which is that common language, that common instruction that all of these computing at the edge and in the cloud are leveraging, both Linux and Windows and other, to be able to make it a more robust ecosystem. So we do collaborate in many ways. Another area where all of us get together is around security protocols and security standards. When you go to a NIST meeting on 5G security, or you go to a NIST meeting on next post-quantum cryptography, we're all there. And oftentimes if one of our people is there and they say, you know what, AMD isn't there, you should call this guy at AMD, make sure he's there. Because what you don't want is an algorithm implemented in a way that doesn't work for everybody, because then it just doesn't work at scale. So we actually cooperate with all of the large silicon manufacturers and silicon providers on many of things like standards, like performance, like security. We each have healthy competition and we all want our stuff to be the dominant player, but we also recognize that from a software and from an end user perspective, you want commonality, you want ubiquity. And so we have to cooperate together with the broader industry and the software providers that run on multiple systems to make sure that their stuff will run on all systems. So it is a lot of competition. And in certain spaces like security standards and protocols, we are all there together and we bring each other together and make sure that we can get that right, because you don't want bad security out in the marketplace.
No, for sure. And the internet was never designed with security in mind.
No, it
So
was not.
it's going to come from somewhere. I'm curious, the x86 architecture, that's been around a really long time. Is it incrementally just improving, or is there a point where we go to a new architecture, or we run out of, not say run out of space, but is it so good that you can't replace it?
It's so good that you don't want to replace it. Everything runs on x86. If you think about x86, the reason why it's still here after 40 plus years is because it works and it's ubiquitous. And the industry has invested year over year. Now, every generation of platform that we and our competition puts out advances the capabilities that you put on top of x86. It gives more performance, better optimizations, better security. But as far as a common layer for Windows, for Linux, for applications to leverage, it is the ubiquity is power. And it's not because it's always been here, we're stuck with it. It's actually innovating every generation of computing that comes out. And again, part of the reason why AMD and Intel came together was to make sure that continues for the next 40 years, that we continue to innovate and to also do it in such a way that strengthens the x86 as that common layer. There will be other compute architectures. There's already some really interesting stuff happening in the neuromorphic space, which is a completely different architecture from x86. And it's more of a...
So what does neuromorphic mean?
So neuromorphic is it's been around for a little bit, but as far as hardware implementations, it's a new approach for how you implement certain kinds of algorithms. And it's more patterned after synapses or how our brain works. So it's modeled a bit after how our brain functions. And let's face it, our brain is a very efficient computer. We process things better than any AI with none of the supercomputing power requirements that you typically have. All we need to do is eat 3 meals a day and our brain works fine. It's a very efficient computer. So a long time ago, scientists and some researchers figured out how to model the brain into silicon, into a set of flows, but it's a different architecture. And what we're finding is it's not something you're going to run Windows on. It's not something you're going to play the next generation game on. But for certain kinds of algorithms, especially for recognition algorithms, so think about the object recognition, facial recognition, sensing kind of algorithms at the edge, it actually is a novel and some cases better approach than doing a GPU or some other form of computing, because it's really efficient at being able to do that classification, if you will, of that is Ryan's face because I can put that together and it's not Steve's face, and be able to make that recognition, or that's being able to tell you what spaceship that is there behind you on your shelf. Is really, those neuromorphic algorithms are really good at that pattern because our brains are really good at pattern recognition. And being able to say, I've seen a cow once, I can always recognize a cow, even if it's a different color or a different size or a different species. That is the power of neuromorphic. So we're seeing neuromorphic being applied in a lot of these edge sensing, and really in edge sensing with low swap requirements. That's one area that we're seeing innovation. Another area, like we talked about earlier, quantum computing is a completely different architecture from the standard von Neumann binary approach. That's why we have a new term called qubit, because it's not 1 or 0. It's 1, 0, and a whole lot of things in between. And so that it requires a different way of computing. So I think we'll see advances in these areas, both at the very tip of the spear edge for things like neuromorphic, and then on the large scale, high performance computing where quantum starts to come into play. Those kind of architectures will also drive innovations and new, if you will, standards for next wave computing. But for 90% of the computing that everyone does every day, where you're running Teams or you're running Linux on your system, x86 is the game. And it's a good reason, because it provides the best performance and it provides the best ubiquity of applications that are running there. And Intel, AMD, ARM, all of our jobs are to make sure that continues so that you always get the best experience on your computing devices and in the cloud.
I had a couple of thoughts on that. So the world we live in is so smart. When you talked about the chip on the network card, everything is basically an IoT device in some respects. And I'm wondering how far we are away from all your little devices becoming more and more intelligent, to the point that I suppose they are to some extent already, because you could, in theory, reprogram that chip on your network to do something else. But is there a recycling of these chips? Do they burn out? Can they be reused again? Can we build enough of them?
So those are two different questions. Let's separate them out. The chips that we're using today and the chips that we've been using, it really comes down to what is the application you work with. The reason why people go to refresh their chips or upgrade their chips, they're looking for better performance or new functionality that isn't supported in the legacy. And so we've always had this sort of cycle of refresh, and depending on your industry or your use case, there may be a lag as far as when you decide to pull that refresh. There's a lot of technical debt out there where there's legacy systems still running certain applications because they never needed to be upgraded. But the second someone says, well, I want to take this mainframe application and I want to virtualize it, suddenly you need a new architecture because that old legacy technology can't do virtualization or can't do cloud scale. And so there are drivers for the refresh, whether it be things like doing AI on your PC. That's going to drive a client refresh because now I want Otter, I want Copilot, I want to be able to do some of these interesting use cases. And I don't want to wait for the cloud or have connectivity. I want to be able to do it now on my PC while I'm talking to you. I want that transcription real time. That's going to require, to get the performance you want, that's going to require a refresh.
Well, and I think you do need to have distributed computing.
Absolutely.
And centralized. Yeah, I think you have to have both. I don't think you want to be the other.
Absolutely. Now, at the same time, with having more things intelligent throughout the infrastructure, both computing nodes as well as intelligent devices, whether you want to call them IoT, I think IoT is too limiting because is a robot in a factory IoT or is it an OT thing? It doesn't matter. It's an intelligent device. It's an intelligent thing. By having the compute on those things to be able to not only perform their key functions, but to be able to load new mission functionality or new capability, to be able to upgrade the error detection algorithms onto a factory floor, be able to get better efficiency. What you're going to find is that the investments we're starting to make today in these next generation architectures will actually pay dividends well beyond the initial investment, because not only do I have intelligence, but I have functionality that I can deploy and I can modify into my infrastructure. You mentioned the IPU again. If today I deploy the IPU because I need intelligent routing, and then I decide, you know what, I'm not getting good efficiency out of my intrusion detection system that's 6 appliances sitting in the rack. I want to push that algorithm into that IPU. So now I can take out those 6 racks of servers, save money on that, and push that algorithm right into the input. I can update my existing architecture because that compute node is able to do multifunction. And now I'm doing intelligent routing and intrusion detection on the network edge. Similarly, in our edge devices, today you're doing sensing. Let's say you're doing object detection. You want to add a new sensor. Do I want to build a whole new infrastructure? No one wants to do that. Wouldn't it be great if I had one compute node out at the edge tapped into a camera and then also tapped into an antenna? Now I can do RF sensing and image recognition. I want to put in an IR camera. It's just another plug. That's the model we're starting to get to where with intelligent sensing, intelligent edge computing, I can have diversity of mission. And if my requirements change, I'll give example in California with the forest fire detection. So they started out with heat sensors. And so that's an obvious one. We want to detect the heat signals. But then they saw, you know what, we'd be better served or equally as good served if we had some barometric pressure detection, had a wind detection and others. So I want to be I don't want to have to go start from scratch and deploy a whole new sensor node. What I want is to be able to go to that same compute that I've ruggedized and put out in the forest and plug in another sensor and add new software. Now suddenly I've got that same infrastructure servicing multiple sensors. And now I'm throwing a little AI on there to be able to correlate between what's really hot today. It's been dry for 6 weeks and the wind is going west. I know where I need to deploy the fire crew to start building that barrier. I have better intelligence, which means I have better actionable outcomes.
And that's exactly what I was going with, the sort of reuse or repurposing. As you have these sensors, it's the Raspberry Pi sort of example of customizing your little node of compute power. And then recycling of chips. Is it possible to recycle them, to reuse them?
So I would say that most chips have a very long life. So the burning out isn't really an issue, although if you have something for 20 years, eventually it's going to live its life. But I do think you find in many cases that, and I'll take the cloud as an example. The cloud has got massive amounts of computing, but not every workload needs the best and greatest computing power. So oftentimes in cloud providers, as they're building out the new infrastructure with the latest, greatest chips, and that's where they're going to run the AI workloads, things like simple cache serving, like a cache server for a web, that is a much more simple program. That's where some of the legacy architecture will be moved. It's not actually physically moved, but they'll move the kind of workload based on the compute needs. And in the large scale environments, what you often find is that high capacity workloads go to the latest, lower performing workloads or less costly workloads can go to legacy systems. And that's how their economics work, is they figured out what workloads work best on what compute, or do I need 50 of these workloads to run the same compute that I would run on a big server with the more advanced stuff, but I can get more money for the more advanced applications. And so they do those kind of cost analyses about where to run it. In your laptop space, a lot of times, if you recycle laptops, a lot of times you give those go to schools, those go to place. Eventually, sometimes laptops and computing devices end of life. And that's where, having efficient recycling e-waste protocols where you can extract the raw materials and recycle and reuse is important. But I think a lot of times what we find is that there are a lot of folks in university that want to be able to play with systems and crack them open, getting access to those and being able to, a lot of corporations do that. They'll take the laptops that they're about to swap out and they'll donate them to universities for research scientists or for computer science engineers to go beat up on systems and see what happens.
Well, yeah, look, it's great to have an old machine to play with, especially with older software that has less security, that will holes, et cetera, et cetera. Steve, it's been great chatting about a lot of information. I've really enjoyed it. You've actually answered more questions just by talking than I've been able to ask. So that's great. Anything you want people to know before you go, or if they want to get in contact with you, what's the best way?
Sure. So I'd say that Intel's here to help. And I think one of the things that people often don't realize is that you can come to Intel. We have our information we give away for free. You go to the website, you can learn about next generation architectures, how to build AI. We have developer clouds where developers can go and try out their algorithms on the latest hardware before buying or having to do the investment. So I would say come to intel.com and learn what's available and what's given away for free as far as content and use cases and reference architectures. For people who want to get a hold of me, I'm on LinkedIn. It's Sorin. Sorin on LinkedIn is the best way to find me. And I look forward to connecting with people.
Fantastic. Thanks very much for being on the show. You go listen.
Thank you very much, Ryan.
Thank you for listening to our episode. I hope you enjoyed it. Please share it with your friends and colleagues. Help us grow our network. Please also check out our website at www.valuu.work and our product that's on there. It's something we worked really hard on. We hope that it benefits you.